Okay, can you hear me in the back? The microphone's working? Okay, so now for something completely different and rather simpler, I think. Why did I want to write a new Prettyprinter library? Well, basically, I had been using the Prettyprinter library that has been distributed with Standard ML of New Jersey for the last 20 years or so, and I gradually became more frustrated with it because I found it required too much trial and error to get the results I wanted. And so I decided to look into pretty printers, and so I went back to Oppen and surveyed the literature. And so I have a very simple, pragmatic goal, which is to have a better pretty printer for my uses. I want something that's natural, simple, predictable, and a fairly transparent model. And this is more specifically with respect to PP, which is the name of the Prettyprinter library in Standard ML of New Jersey, and which is derived from or based on the design of the format package in OCaml, which is again heavily inspired by the PPML Prettyprinter Meta Language that was developed in the 1980s at INRIA. Okay, so I wanted to be expressive enough to be able to write the pretty printers that I typically write. And so, of course, one of the first things I ran into was that in the Haskell world, there's the Wadler Lion pretty printer family. And so I investigated that, going back to the Hughes 1995 paper and the Wadler 1997 paper and the source code of the current library and so on. And that's an improvement, but not quite enough. I found that the algebraic development technique led to an algebra of pretty printer constructors or document constructors, which is not quite as natural and simple as I'd like, and I thought I could do better. So this is an advertisement as usual, not a tutorial, so it's going to be rather fast and possibly esoteric to those of you who haven't recently fooled around with pretty printers, so I apologize. So Derek Oppen in 1980 wrote probably the first kind of general paper about a pretty-printer engine, and it was completely imperative, and it was done in the context of the computing of the 1970s, 16-bit computing, and so he was very concerned about the length of the queue of commands that the pretty printer could manage, and so the main algorithmic result was that he could limit the queue length to 3 times the line length. Okay, but that's if you're working in some subset of 65 kilobytes. In the 1980s, as part of, or possibly in conjunction with the Centaur project at INRIA Sophia Antipolis, the PPML language, meta language was developed, and this had some new ideas. The idea of boxes, which was basically inspired by Knuth's boxes in tech, and the idea of conditional line breaks, which were also implicit in Oppen. And the boxes could have an alignment property, so alignment was another idea. And then Hughes and Wadler in the mid-90s, the big idea was that there would be an intermediate data structure that they called a document. I call it a format, which you build. So the typical thing in Oppen was that you had some kind of annotated text with some kind of annotations that might impose some kind of block structure on the text. And so you're going from text to text. And in most pretty printers, we're interested in having some data structure and pretty printing it for diagnostic purposes or whatever. Anyway, another aspect of this, so the document idea as an intermediate structure is the main thing. And then Hughes in particular gave this as an example of a serious algebraic development of an algorithm. And that's nice, but I'm not convinced that the algebra that he derived was the most natural and intuitive. And of course, this was done in the context of Haskell, so lazy evaluation was invoked as part of the algorithm because it's basically generate all possible layouts and pick the best one. And generating all the possible layouts might be expensive if you didn't use lazy evaluation, but I and several other people have managed to translate the Wadler algorithm into a strict form in standard ML, for instance, and so laziness is a kind of red herring. It's not necessary. Okay, so this is just a picture summarizing the two models. With Oppen, he was trying to save space, so he was generating pretty printed output as he consumed the input in an online style. And the print engine was entirely imperative. You're basically generating commands that the print engine would execute. In the Hughes and Wadler model, you have a two-stage process where you first write a formatter function which takes whatever data you want to print and turns it into a document or format, as I term it. And then there's a rendering function that takes that format or document and generates output, or possibly some layout representation that might be a data structure, but basically, what you're going to see on the screen. Okay, so I'm mainly interested in generating or writing pretty printers for a bunch of data structures, which are typically, in my case, abstract syntax trees, types, module signatures, various intermediate representations in the compiler. And in particular, I'm not trying to develop something that will compete with typical textual layout utilities like Markdown, ASCII doc, LaTeX, and so on. So the main ideas are blocks, which are like boxes. They're basically either simple atomic pieces of text, which will be printed as such, or combinations, hierarchically nested compound things. And these in PPML were called boxes, following Knuth. And I use the term block, which comes from Oppen's original paper. These blocks are formats, which in Hughes and Wadler were called documents. So another basic idea is that we have breaks separating at the lowest level, separating pieces of text. And the break is either a space or n spaces, or it could be a soft line break, which means that it's an optional line or conditional line break, which might be triggered if you're running out of space on the line. Or it might be a hard line break, which means an unconditional line break. And then there's alignments, which are specifications of how things should be arranged within a block. So there's compact and horizontal, which are basically horizontal arrangement, but compact puts no spacing between the elements, whereas horizontal puts a single space between them. Or vertical alignment, or packed, which is you start filling in the line, and when you run out of space on that line, you return to the beginning and fill in the next line, and so on. So it's like a paragraph justification. And so one of the things we have to do is determine whether we're running out of space on a line. So that's the fundamental conditional driver. And so we need to know how much space the next thing we want to do is going to take, and whether we have room for it on the current line or not. So that I call a measure of a block or a format. and I've got to keep this awake. Okay, so the measure of a block is going to be very simple and very conservative. I just measure it as though it was going to be laid out on a single infinite line, suppressing all line breaks, even hard line breaks. Okay, so that's a very crude and conservative measure, but in practice it seems to be okay. And then another point here is that we're in the process of filling in a line. And so we're basically looking at the current line and the things to be coming up to be laid out on the current line until we have to go to the next line. And of course, once we go to the next line, the current line is finished. And so it's a very narrow, one-dimensional view of the arena in which we're playing. So here's some code. This is the definition of breaks, alignments, and formats. So breaks, as I mentioned, are hard, soft, space, and a null break for completeness. Alignment is C for compact, H for horizontal, V for vertical, P for packed. And then a format is defined by these 7 constructors. The primitive formats are empty and text of string. Okay, so those are atomic. Then you have 2 flavors of block. You have a general block, or basic block, which is just a list of elements where an element could be a break or it could be a format. You know, there's missing union data type for that. And so in that case, the breaks are explicit in the definition of a block, and you can put them where you like and what flavor break you want, etc. So this gives you kind of a free-form way of constructing blocks. But most of the time, you're going to be using aligned blocks, where you specify just the format list and an alignment, and the alignment determines an implicit break between the elements. So if I do an A block with alignment compact, that means that there will be no break separating the format elements. They'll be just laid out contiguously. And so on with the other alignments. And okay, so a critical issue is indentation. So this is where Hughes and Wadler are both weird and unnatural. And so I just wanted to have a simpler and more obvious notion of indentation. And so I say, if you have a format, you can indent it so many spaces. And that indentation applies to the entire format, not only the last all but one line or something like that. So indent is just a modifier of blocks, of formats. And then there's another modifier called flat, which is just saying that no matter what's in this format, I'm going to lay it out flat. By laying it out flat, I mean I'm just going to string the individual strings or text items out on the line horizontally. So it's a kind of brute force flattening. This corresponds to the group function in Wadler. And then finally, so we have one source of conditionality in that we have these soft line breaks, which can get triggered as you're running out of space on the line. The other form of conditionality is this alt. It's basically an OR for formats, and it says if the first argument fits, lay it out. If it doesn't fit, try the second argument. And you only get 2 chances. Okay, so this is just a very schematic picture of what a laid out format. This is not the format per se. This is a particular layout of it. And the kind of reddish little boxes correspond to triggered line breaks, soft line breaks that are triggered. And there may be others, but only the ones that are triggered are displayed here. And then the blue boxes are hard line breaks. And there's, any block will have a left margin, which I call the block left margin. And overall, this RM is the right margin, and that's determined by the line length parameter that's driving the whole thing. The global parameter is the line length. Okay. Right, so conditional rendering again. At a soft line break, which could be like an ordinary block with a soft break in it, you're basically going to measure the following format, and if it fits, you just continue, or if it doesn't fit, you break the line and start on a new line. Now, when you break the line, you start indented to the current block left margin. Okay. So block left margin during rendering, the rendering process is a kind of part of the state that is maintained. The other one is if we have an alt, there's a function form of the alt constructor, lowercase alt. And if I have a format of the form alt format 1, format 2, as I said, we render format 1 if it fits, and otherwise render format 2. So that's it. As I mentioned, this flat measure is a key idea. We can get away with this really crude, conservative measure of the next thing to be printed, the next format. And the other point is that also to keep things simple, I'm assuming I'm worked in a monospace font. Even if there might be UFT8 character encodings or something like that. There's a device that's added to deal with UFT8. UTF-8? UTF-8, something like that. And so all the measurements are just in character counts. That's another place where we don't have to try to follow LaTeX and be fancy about measuring things. So the indented format, the two things to thing is that the indent operation is just modifying an existing format. It's not a format on its own. And indentation is activated only when you're starting on a new line. In other words, after a line break. It's basically doesn't really make sense to indent something that's going to be printed in the middle of a line. So indentation is inherently a property that only makes sense after a line break. And so that's reflected by that rule. So an example, in Wadler's papers, he has a couple of variations on prettyprinting a tree data structure. So this is a very simple data structure. N is a node constructor. Node has a string and a list of trees as children, and we format it using these two functions. So C block creates a compact block with no separators, no breaks, and here I'm using some of the interface that the library provides is fairly rich. We provide a whole bunch of functions that people would have to reinvent on their own as soon as they start writing a pretty printer. And so to prevent that, we have things like brackets, V sequence, which is a vertical sequence, taking a comma format, which is just a text format with a comma in it. So it'll print these formats vertically, and with each format followed by a comma. And so that makes it pretty simple, and then I use map over format tree to get the children formats. And here's an example of a particular tree 1. And then if I format that tree and then call the top level print format new line, it'll print that. Okay, so I won't expect you to completely absorb the code in the example online, but anyway, that's a fairly trivial, simple example that shows you how it works. And it works quite well as you scale up to real-life examples. Okay, so at the moment, I need more experience. The main experience here was that I developed this library over about 10 plus iterations, and I have re-implemented 11 non-trivial pretty printers, like for types, abstract syntax, the Flint intermediate representation, CPS, flow graph representation, et cetera, et cetera. So there's a bunch of not non-trivial pretty printers in the system. So I re-implemented those using this library, and that worked. And it's a pretty straightforward translation, because the structuring notions that come from PPML that are built into the older PP library translate naturally into these vertical, horizontal, packed block structures. And we need further testing and tuning, which is why we want to get this out to the world and get feedback from external users. There's a couple enhancements. John Reppy's version of the Pretty Printer was similar to the OCaml format, but he added style text, which is basically the main way of thinking it is you're printing to an ANSI terminal, and there are certain character codes you could send to the terminal that turn things red, or italics, or bold, or blinking, or whatever. And so there's one model of style text which allows you to produce interesting looking text on a ANSI terminal. There's another way of, in my case, a separate renderer that can translate into, say, HTML. The current case is it translates it into HTML3, but it could be updated to use HTML5. Then there's a variant of a text string, which is called a token, which allows you to put in a string with UTF-8 encoding, and then separately specify how many, what its length and character count is when it's printed. So again, we're still assuming in such a case that we're in a monospace font. So there's a set of monospace fonts that allow a certain set of UTF-8 encodings. And then potentially, well, there's another way of controlling the conditional line breaking, which is a ribbon percentage. It says how much of the line should be text. Should no more than 50% of the line be text, and so that's a way of a secondary way of limiting the amount of space you're allowed on the line. And it's trivial to add that. I don't have that in the system now, but it's a trivial change. Another more interesting one is some kind of tabulation, basic setting tab stops and tabbing to them. There's a very simple way of doing that I haven't implemented yet. But then Sam Westrick, in his SML format tool, has a pretty printer that includes an idea of fancy tabs, which are called, lexically or statically scoped tabs. And so I want to investigate that. I suspect that is probably compatible with this design, and if so, it'd be interesting to experiment with that. But again, I need more experience, more examples to drive what's necessary in terms of pre-printing expressiveness. At the moment, I've got a very simple system, and it does what I need, but other people might disagree. Okay, so in conclusion, I've got a simple model with a few key ideas: nested blocks, alignment, conditional line breaks, indented blocks. And a very simple implementation. It's purely functional, written in standard ML, quite small, and no need for laziness. Of course, eventually things go off to some device to be printed and imperative stuff happens. Is it efficient enough? I think so, but my impression is that it's basically a linear process. You have a data structure of such and such a size, you translate it into a format which is roughly linearly related to the size of the original data structure, and then rendering is also essentially linear. Again, because your scope of look ahead is very limited. You're just looking at how much space have I got left on this line. That's not a whole lot. The other thing about efficiency and optimality is this is producing human readable content, something you're going to display in a terminal or a page, and you're not going to generate 1,000-page long pretty prints. You're mostly going to generate half a page pretty prints or 1 page pretty prints, and if it gets too big, you resort to some kind of depth limited printing, which was invented back in 1975 or so at INRIA. Just cut off the printing of the structure at a certain depth. And as I said, it's a simple batch of code, easily ported to whatever. Question? Oh, wait. One more important slide, if I can. This is where you find it, and the source and documentation, including soon a fairly substantial tech report with a lot of background and details and so on. Questions? I'm a little bit over.
Well, one quick question. Hi, Dave. I'm
Hi.
Sam, by the way.
Oh, Sam. Hi.
Yeah.
Nice to meet you.
So when I was developing SML format, I ran into all sorts of interesting challenges for doing pretty printing for a full-scale programming language. Mm-hmm. And obviously, your use case is a little bit different here. But I'm just curious, do you think that this technique that you've developed could scale to printing an entire grammar for, say, standard ML or a full-scale programming language?
I guess so. I don't off the top of my head see why not. Again, a lot in the very earliest days, the idea of pretty printing is that you had, say, a Pascal program, and it was laid out poorly by some student, and you wanted to put it through a machine that would relay out the Pascal source code in a prettier way. And you could do that with SML code too, but then you might be dealing with larger quantities of input than is typically the case in these cases I mentioned. So that remains to be seen, but I'm guessing that it'll handle it.
Okay, thanks again.
Okay.